What I want to do is really talk about three, I think, prevalent fictions in the field right now. Certainly, if you consume at all sort of longevity influencer stuff on the internet, you will have heard these. And unfortunately, we see some of these fictions showing up in the scientific literature even, which I view as problematic. And then I want to talk about three of the core facts in the field that I think really set the foundation for where we're at, the trajectory going forward, and why science in this area is so important. You may be asking yourself, like, of all the things Matt could have talked about in a TED Talk, why would he pick this topic? And I've been in the field doing research on the biology of aging for almost 30 years, which is just to say I've seen a lot. It is the most exciting time I can remember in the longevity space in all my years in the field. The science is maturing. We are at the point where we're seeing drug development through traditional biotech pipelines and even movement into the clinic. And of course, lots happening on the basic science side. Along with a surge in popularity over the last 5 years that is almost breathtaking. But along with that enthusiasm and excitement, there come some challenges. And again, I think we, in some ways as a field, have a credibility challenge. And so I just want to use this platform to hopefully communicate to my scientific colleagues or any of you who care about data and evidence that I think particularly the scientists, the scientific community, we need to be very precise in our language, rigorous in our thought, and not mislead people. Because if you mislead people, and they realize you have misled them, you're going to lose trust. And I'm concerned that we've already done some damage to our reputation. So that's why I think it's so important to be precise in the way we talk about our science. Okay, so I'll start with fiction number one. You've probably all heard this. Fiction number one is that we are close to solving aging or curing aging, or that aging is optional. It's not, we're not. I think that's important to appreciate. I think, again, there are many ways to illustrate this. It should not come as a surprise to anyone who's actually paying attention that we're not close to solving aging. I think one way to appreciate this is just to ask the question, if we look at our ability in the basic research world to slow aging, increase lifespan, improve health span, are we continually year over year getting bigger and better? And the answer, unfortunately, is no. So this graphic is from an experiment that was done in a book by Rick Weindruck and Roy Walford about 40 years ago. So this is an experiment where they treated mice with 65% caloric restriction, looked at a variety of health span metrics. If you're interested, this book, The Retardation of Aging by Caloric Restriction, is sort of fascinating for a 40-year-old book. Look at all of the health span metrics that they showed caloric restriction can positively impact and the extent to which it can impact those. This is just a lifespan experiment, 65% caloric restriction. I just want you to appreciate the absolute length of time the treated animals lived. So the median for the treated animals was about 50 months, almost 50 months, and the maximum was getting close to 60 months. That may or may not mean anything to you if you're not a mouse lifespan person. But the next time you look at the literature and somebody's telling you about this amazing result they got extending lifespan, just look at the absolute values of the lifespans to kind of get a feel for where does it fit. Okay, so all I've done is taken the liberty to take that same data, put some colors on it. This is exactly the same data I just showed you. Now I'm going to show you some of the things people in the field are really, really excited about today, with good reason, by the way. The second best effect I'm aware of, non-genetic intervention, lifespan effect in mice, is an experiment we did in my lab about 10 years ago where we treated middle-aged mice for 3 months with rapamycin. You may have heard about rapamycin. It really is the gold standard for a drug to slow aging, again, at least in laboratory animals. You can see it's not as good as caloric restriction. So the red line compared to the purple line. It's about maybe half the absolute increase in lifespan. That's the second best we've got in the field right now. Again, rapamycin, very powerful. I think it does have benefits for humans. Probably does for dogs as well. But it's not as good as caloric restriction. We heard about epigenetic reprogramming. There's the data. Not even as good as rapamycin. So it doesn't mean we can't get there. It doesn't mean that's the best. But right now, that's the data. If you care about data, you've got to be honest and say, doesn't seem like it's going to be better than caloric restriction, at least right now, for effects on lifespan. Same thing's true with health span. We can go down the list. There's a lot of things that have been reported to extend lifespan in mice. One interesting example, and some of them are natural products, one interesting example is nicotinamide mononucleotide, or NMN, an NAD booster. You can see by the red line here, the apparently reported long-lived NMN-treated mice don't even live as long as the controls, the untreated animals in the Weindruck and Walford experiment. Okay, we don't know why that is, but it's hard for me to feel really confident that this is a robust result, right? And in fact, as a scientist, I'd be embarrassed if I was hyping this or selling it to consumers who may not be able to evaluate what's real and what's not in the scientific literature. So we can look at a bunch of stuff, and I didn't put everything up here, but you've heard of senolytics probably, you've heard of IL-11 maybe. Again, the point is nothing is better than the caloric restriction experiment from 40 years ago. And again, this is important stuff. Like, there's a lot of value in having many different ways to slow aging in animals, and we can move that into the clinic, and we can have impacts on people's health and longevity. The only point I'm really trying to make here is, if we were really getting close to curing aging, wouldn't we be able to get better and better and better effects on lifespan in animals? So this is sort of my take, and I may be sort of taking this a little too far. I kind of think we understand the biology of aging about the same way that people understood the surface of the Earth in 500 BC. So this is a map called Hecates's map from 500 BC. It's got sort of a Libya thing and a vaguely Europe-shaped thing and an Asia that doesn't look at all like Asia, and you sail too far and you fall off the edge of the Earth, right? Maybe we understand aging biology better than that, but we don't understand it completely. And there's a couple of points I want to make about this map. Number one, we need to explore around the edge of the Earth, right? We need to try to go off the map and figure out what we don't know about the biology of aging. I think that's how we get to very large increases in lifespan and healthspan. We need more discovery science in this field. Number two, in 500 BC, this map was really useful, right? You could explore, you could trade, you could make war, you could get rich, right? And I think the biology of aging as we understand it today is also really useful. We can do important stuff. So I don't want to diminish that potential, but we need to figure out what we don't know. Okay, so fiction number two, aging has been reversed. No, it hasn't. No, it hasn't. It blows my mind that this even really needs to be said among scientific community. What would true reversal of aging look like? What would that look like? We would be able to take an old person or an old mouse and make them young again. Nobody's done that. We can reverse some features of aging, right? We can reverse a subset of features of aging. And again, that's important. Improving function in tissues and organs is valuable. We have not taken an old mouse or an old person and made it young again. I'm sorry, Brian Johnson is not aging in reverse. Doesn't even pass the eye test. David's mice are not aging in reverse. Those aren't even wild-type mice. So again, I think being precise in our language is really important. Improving health is valuable. Improving health is not reversing aging. Okay, fiction number three. Clocks measure biological age. Okay, so this, I think, it's understandable why people get confused and why scientists use this terminology a little bit sloppily. You see in the literature all the time in titles and abstracts, my clock increased biological age, reduced biological age, measured biological age. Clocks don't measure biological age, okay? There are a lot of different clocks out there. I'm going to talk specifically about the epigenetic clocks because those are the ones that probably most people are most familiar with. So what do they actually measure? They measure average methylation status at specific regions in the genome, usually a few dozen. That's what they measure. They don't measure biological age. And then the specific regions where the average methylation status is quantified will correlate to something. Doesn't even correlate directly to biological age. Usually, depending on the clock or the algorithm, it'll correlate to chronological age. It'll correlate to mortality risk. That's informative. It'll correlate to your risk of developing a specific age-related disease, or in rare cases, it will correlate to the change in health over time. These are all done based on population studies. Each of those things correlates to biological age. So at best, these clocks, as they're used today, are a correlation to biological age. They don't measure biological age. And they're really valuable in the research world. I think these tools are helping us, to some extent, understand what aging is fundamentally, when it starts, how it changes throughout the life course. Potentially, they'll be useful for clinical trials in the relatively near future. At this point, though, I don't think they're ready for prime time. And I think one of the unfortunate things that has happened is the rush to market in the consumer space with these direct-to-consumer epigenetic age tests where we really don't know precision or accuracy, and they're not clinically actionable. So I did an experiment, this was maybe a year ago now, where I got 8 different tests from 4 different companies, so duplicate replicates of each one, did those on myself, same day, same samples, and just sent them back in. Just because I didn't know what the precision would look like. And it's not very good. So I was in my mid-50s. I am in my mid-50s. The results I got back ranged from the early 40s to the early 60s. 20-year difference, okay? Standard deviation of 7.5. This is all noise, guys. So I think that's a problem, and I think it's a real problem when scientists are selling these things. I think it's also a problem when doctors are recommending these things to their patients. In my opinion, a medical professional should never, ever recommend a diagnostic or a test. They don't know the precision, they don't know the accuracy, and it's not going to improve care for their patients. So the fiction is that these clocks are measuring biological age. Okay, so let's go to the facts. Fact number 1. Aging is a modifiable biological process. And I want to focus on both of those words. So let's start with biological. All that means is that aging is under the control of genetic and environmental determinants. And probably most people in this room already appreciate this, but if you don't, I think dogs are a really easy way for people to appreciate this concept of biological aging. We're all sort of familiar with the idea. 1 human year is about 7 dog years. That's just a way of saying dogs age biologically about 7 times faster than people do. They get the same age-related diseases that we do. They show the same functional declines that we do. It just happens faster. So that illustrates the point that aging is a biological process, and the rate of aging is different across different species. The cool thing about dogs is because we've got this large body size difference, right? Just think about the difference between a Great Dane and a Chihuahua. We can also see the individual variation in aging rate. So big dogs, it turns out, age biologically faster than small dogs do. And so this makes the point, just like in humans, different individuals within the same species age at different rates. And it's just a genetic and environmental condition that determines the rate of aging. Okay, modifiable, right? So I'll just go back to the graphic I showed before. We've got many different ways in the laboratory that we can change the rate of aging. And when we do that, we see that most, if not all, functional declines that go along with aging and diseases of aging are delayed in animals. We haven't yet proven that we can do this in humans, although I think if you look at lifestyle, you can make a pretty good case. The reason why eating a healthy diet and exercising regularly and sleeping well and having human relationships seems to slow all of the functional declines and diseases of aging is because those things are, in fact, modifying the biology of aging. Okay, so fact number 1, this is really important. Hopefully we can get everyone to understand this. Aging is a modifiable biological process. And that leads to fact number 2, which is that as we understand the biology of aging and we can target it, that's going to be way better for human health than what we've done in the past, which is waiting until people are sick and trying to target their individual disease in isolation. The impact from targeting aging is orders of magnitude greater than targeting individual diseases. It turns out, if you look at the top 10 killers in the United States, 9 of them have biological age as their greatest risk factor. And as we've already heard today, when we're successful at slowing aging in people, that will have an outsized impact on health span and life expectancy compared to curing individual diseases in isolation, curing cancer, curing heart disease. So again, this I think just makes the point why research in this area, clinical translation in this area is so important.